All right, so last time we talked a lot about critical points, and that was where the first derivative equaled 0. So today we're going to talk a lot about inflection points. This is where the second derivative equals 0. However, when you set the first derivative equal to 0, whatever you get, that's a critical point. Period, end of story, no matter what, those count as critical points. When you set the second derivative equal to 0, it only counts as an inflection point if the graph changes concavity. And I bring that up and everyone like thinking about cavities in their teeth. Concavity is, it's like concave up or concave down. Have you ever heard of like concave and convex, like the direction something is bending? That's what this is. It's the direction that the graph is bending. And so we're going to add on to our little cheat sheet that we had here. So I'm going to write what we had last time, where the original graph is increasing, the first derivative is positive, decreasing means the first derivative is negative. And so here's the deal. If that's true from here to here, that's going to be true anytime you take a derivative. So it's also going to be true from here to here. And then it would be true from here to here. And if you kept on going, we're not going to do it. There's no third derivative test. So we're not going to go any farther. But if this is true from f to f prime, it's going to be true from f prime to the second derivative. So increasing positive, decreasing negative. And then the second derivative tells us about the concavity of the original function. So here's what it is. If your second derivative is positive, that means your original graph is concave up. And we just abbreviate that, concave up. And where the second derivative is negative, your original graph is concave down. So it makes sense. Positive is up, negative is down. Let me draw a few quick sketches of what this can look like here. If this is your graph of f of x, you can have something that is concave up. So that would be like a smiley face. That's concave up, like a cup that you could pour water into. And say this is your inflection point, and that's where it changes to concave down. So that would be an example of an inflection point. So graphs like sine and cosine, those waves, they have tons of inflection points in them, infinitely, forever and ever, because they keep on waving. So you have concave up, and then this is the inflection point, and that changes to concave down. So that's an example of like, yes, that would be an inflection point. But if you have something that's concave up, and then it changes to just linear, it changes to a line, that does not count as an inflection point. It has to actually change from concave up to concave down or vice versa. If it changes to linear, that will not count. And so that's what it would look like if you're looking at f of x. If you're looking at f prime of x, now that's this one right here. So instead of concave up to concave down, the graph would change from increasing to decreasing. If we're looking at the derivative graph, where the original one changes concave up to concave down, f prime would change from increasing to decreasing. So if you have something like this, that would be an example of an inflection point. Like, yes, that would be an inflection point. But if it changes from increasing to constant, that does not count. This would not count as an inflection point. You're probably like, why is she hitting this so hard? Because one year, not so long ago on the AP exam, they put a graph up there that had all these constant sections. And then they asked about how many inflection points there are, and none of them counted. There was only like one spot on the graph where there was an actual change. And I know that a bunch of my students probably missed that because they probably counted those as inflection points. So I try to like hit that really heavy ever since I saw that. You have to actually have a change from concave up to concave down or vice versa. These don't count. Okay. So if you have a critical point, if C is a critical point, and that means derivative equals 0. If you have a critical point, derivative equals 0. If your second derivative is positive, that means the graph is concave up. It'll look like this. And that means that C is a relative minimum. So if you have a critical point and the graph is concave up, that means that C has to be, oh, I'm sorry, C is not a relative minimum. C is a location of a relative minimum. I am so sorry. Location of relative minimum, because they'll get you on that too if you word it wrong. It's just the X value. And if the second derivative is negative, that means that the graph is concave down. And so you get that high point, you get that peak, and C is the location of a relative maximum. I'm just going to write that because if I try to write the whole sentence, I'm going to run out of space there. But you end up with a high point, so a relative maximum. And if your second derivative is 0, then you can't make a conclusion. That means you don't have any concavity. That means your graph would be linear. It's not bending either direction. So we're going to take this function and just go through the entire process beginning to end. We're going to find intervals of increasing, decreasing, relative maximums and minimums, absolute maximums and minimums, inflection points, intervals of concavity. We're just going to find every last thing. All right, and we're going to practice our justification. So find the critical values. That is derivative equals 0. So this derivative is 3x squared plus 6x minus 9. And I'm going to divide everything by 3. And then that is going to split x plus 3, x minus 1. And so our critical points are -3 and +1. All right, so letter B, find the intervals where the function is increasing and decreasing. So I'm going to make a number line for each one of these factors. So we've got x plus 3, we've got x minus 1. And so this is going to have a critical point at -3. This will have a critical point at 1. They're both going to be negative and then turn positive. And again, you can always pick a test number to try. So slicing up the number line, we're going to get the overall sign negative times negative is positive. And then this middle section will be negative and then positive. So if we're going to write where f is increasing and decreasing, f of x is increasing. And again, you want your statements to be f of x is or f of x has, because f of x is the function you're talking about. You're using f prime as like your source that you're citing. That's like the guy that you're quoting. So f of x is increasing on these two sections. So -infinity to -3, union 1 to infinity, because f prime is positive there. Thought I could make it fit, but I couldn't. And then the sibling statement is going to be f of x is decreasing everywhere else for the exact opposite reason. So decreasing would be -3 to 1 because derivative is negative there. All right, and then locations of the relative extrema. All right, we already have the number line, so I can just look back at that. At -3, we have a change from positive to negative. So hey guys, does that mean relative maximum or relative minimum at -3? Maximum or minimum? What do you guys think? Maximum, good. Nice job, guys. Positive to negative means relative maximum. So f of x has a relative maximum at x equals -3 because f prime changes from positive to negative there. Here, and I'll separate these. This is from the previous problem. All right, and then a statement for 1, we have the derivative changing from negative to positive. That means the location of a relative minimum. So f of x has a relative minimum at x equals 1 because f prime changes from negative to positive there. Right, and then absolute extrema, that is your candidates test. And we're given this interval. So we're going to have these endpoints and our critical points, and we're going to plug them into the original function. So make sure you plug them into the original function. That's this guy right here. So we've got -4, and then our critical points, we have -3. Oh, and actually, we're not going to get to include 1. How come I don't have to include 1? I get to skip that one. How come I'm not going to put that on my chart? Yeah, good. It's above 0. It's not in this interval. 1 does not fall in this interval. So so it doesn't count. So we're going to skip that one, which is cool because that's less work. All right, so let's plug in -4. All right, -4 cubed, that would be -64. -4 squared would be 16 times 3 is 48, so plus 48. -4 times -9 would be 36, and then plus 4. All right, so let's see. 36 plus 4 is 40, plus another 48 would be 88. So we've got 88 minus 64. Again, you know, you can work it out in your head, you can count on your fingers, you can write it off to the side, you know, but some way you got to be able to get through it. All right, so let's do -3. -3 cubed would be -27. -3 squared would be 9 times 3 is 27. Oh, that's convenient. So those are going to cancel. -3 times -9 will be 27, and then plus 4. So that'll be 31. And then if we plug in 0 for all these x's, we're just going to get 4. Now, I don't have to write a because statement because the chart acts as your justification. So we just need to write the answer. So absolute maximum is 31 at x equals -3. And the absolute minimum is 4 at x equals 0. And again, you want to get in the habit of writing the whole statement because sometimes they ask you for the maximum or minimum, and sometimes they ask you for its location. And if you just write the whole thing, then you don't have to worry about it. You know you've answered the question. And this is like pretty much guaranteed to show up on the AP exam. They ask it every year. So that's actually a review of everything we did last class. This is the new part. Find the inflection points. All right, this is going to be second derivative equals 0. So let me go back to our first derivative. First derivative is right here. This 3x squared plus 6x minus 9. We're going to do the derivative of that. So that would be 6x plus 6. We're going to set that equal to 0. So we're going to subtract 6. And so we get x is -1. Now here's the thing. When we do first derivative equals 0, these are critical points, period, end of story. Those are just critical points. We don't have to check anything. Whether they are locations of relative maximums or minimums doesn't matter. They just are critical points. And yes, if you wanted to factor out the 6 instead, you'd be left with x plus 1, and you would still get -1. So however, whatever was your personal preference to get through that, you'll still get the same answer either way. But we need to check if this is actually an inflection point. You have to have a change in concavity. So I'm going to make a number line for this second derivative. And again, if you wanted to factor out the 6, you can. Then this would just be x plus 1. But this is going to be negative and then turn positive. So this is, in fact, an inflection point. We're going to have a change in concavity. The graph is going to be concave down and then change to concave up. Again, negative means down, positive means up. It makes sense. It's logical. So find the intervals where f of x is concave up and concave down. I kind of just said that. We're going to say f of x is concave up from -1 to infinity because the second derivative is positive there. And for the second derivative test, the second derivative is your source that you're citing. So like this is the guy that whose information you're quoting. Second derivative is positive there. It's like the exact same statement we did for increasing and decreasing. It's really not like any different in the setup. You're just using the second derivative instead. And then f of x is concave down -infinity to -1 because second derivative is negative there. And once again, these justifications are not going to change. Like those are the answers. Those will be the answers on your test. Those will be the answers on the AP exam. It's just by definition, so that can't change.